Section 17.2, constructive and destructive interference of sound waves. So as mentioned, we're going from thinking about just general waves like on a slinky to thinking about sound, because that's something you hear every day, right? So we could imagine if you have a sound system, right, a stereo that has two different speakers that have an identical input. If you stand right in the middle of those two speakers at an equal distance from either one, then what you'd find is that the wavelengths coming out of one would meet the wavelengths coming out of the other at exactly the same points, at the same rate, right? So here we have condensations drawn in and rarefactions. Condensations, right, where the air molecules are closer together, rarefactions where they're spread out. And notice at this point at 3 meters, two condensations have met, they've overlapped together. So if you imagine those are both positive peaks, they've both gotten larger, right? The condensation's extra strong. The rarefactions also are about to meet as they come to the observer. So the low point is going to get extra intense. So if you have two waves that meet condensation to condensation, rarefaction to rarefaction, we say that they are exactly in phase. And this is known as exhibiting constructive interference. So that's a key term here, right? This idea of constructive interference, and that it occurs when they're exactly in phase. And that's demonstrated here in this schematic graph of a pressure amplitude versus time from each of the two speaker sources, right? So each of them individually puts out this nice little sine wave going up and down, but they're exactly in phase, so they look identical, right? When one of them is at a peak, one of them is at a positive peak, the other one's at a positive peak. Guess what that means when you add it together? The amplitude is twice as big because it has two positive peaks in there, right? Similarly, the low points, they're both at that same low point together. So the lows are extra low. They're twice as low, right? So the result is that the sound is twice as loud because the pressure amplitude is what corresponds to loudness. You hear a loud sound when you get this constructive interference of two waves that are in phase. Now, this is going to occur anytime you're at an equal distance from each speaker and the speakers are identical. What about if we offset one of them? So that's what's shown here. If I move one of the speakers back by half a meter, which ends up being half a wavelength for this picture, now notice what happens on the meeting point. We have a condensation still from the right speaker, but the left speaker is now at a rarefaction. And sure enough, when we get a rarefaction from the right speaker, we're going to now get a condensation from the other. This is known as being exactly out of phase. And the result is going to be what's known as destructive interference. So we still have, from the right speaker, we have our normal up and down sine wave, but the left speaker is flipped, right? We have it goes down then up. So we have the ups meeting the down at the same point. The down is meeting up at the same point. What does this mean? When we sum these together using our principle of linear superposition, they're going to have destructive interference, where it's not the waves are gone, but you're not able to hear anything. There's no sound at that point. So even though we still have technically the waves both present, the amplitude is zero. It's quiet, which is really strange. But you can demonstrate this if you have two speakers with a truly identical signal. Or another place that you may have already seen this in action or heard this in action is if you have some fancy headphones, right? Noise canceling headphones, the way that they work isn't just magic. It's not that they just turn off noise. Rather, they take the input wave as it comes in, and there's electronic circuitry that figures out what that wave is coming in, and it has its own speaker to emit a wave that is exactly out of phase with the outside ambient noise. Since it's emitting something that's exactly out of phase, it produces destructive interference. and it can greatly reduce the noise level, especially if it's something constant, like the drone of a jet plane, right? That's something that's easier for the noise canceling headphones to pick up on than conversations are sometimes variants, right? So it's a little harder to match in real time. But it still is able to reduce the noise level greatly, and it's because it's taking advantage of destructive interference. So I don't know if you realized it, but the way your noise canceling headphones work is they actually put more noise out in order to cancel the noise. There you have it. All right. So if the wave patterns don't shift relative to one another as time passes, the sources are said to be coherent. That's something I think every problem we have, we're going to assume the sources are coherent, that they aren't shifting as time passes. This just means that we have them nice and steady, right? So we don't have to worry about a phase change in the middle. Once the phase is set, it's set. And so once we know we have coherent sources, then we can start thinking about the different places that they met, right? Before we just looked at one particular point, but really you could map out a whole field of where will the sound be louder and where will it be really quiet, right? So if we have a condensation mean a condensation, it's going to be a loud point. That's shown with these red ones, or rarefaction mean a rarefaction. These are all loud. And then if you have a condensation meeting a rarefaction, these are going to be, I'll get a different color. These are going to be the really quiet points where there is no sound directly. And it's something that in audio engineering you really care about, trying to avoid having dead spaces where there is no sound. So, but it's something that can happen, not usually desirable. So how do we determine where in this mapping out we would have loud sounds versus no sounds? Well, it turns out the key is going to be the path length between the two speakers. So if you have two wave sources that are vibrating in phase, if they're just the same signal, that's going to be our standard thing. Then if you have a difference in path lengths that is 0 or an integer number of wavelengths, that's going to lead to constructive interference. If you instead have a difference in path lengths that is a half integer number of wavelengths, then that will lead to destructive interference. So that's a lot of words. I tried putting the words into an equation form because I find that helpful to think about. But if you prefer writing out the words, that's totally fine. So for constructive interference, d2 minus d1 is equal to m lambda. So we could draw that out here on this particular one, right? We could say call this one d1, and then the distance from the speaker to that same point, we could call d2. We're just looking for the difference in path from one speaker to the point and the other speaker to the point. So d2 minus d1, if it's constructive interference, is equal to m times the wavelength. For destructive interference, that path length difference, d2 minus d1, is equal to the quantity m plus 1/2 times the wavelength. And m here is just an integer. So from 0 to 3, and so on and so forth. So this is a great rule of thumb for determining if we have constructive interference, if it's a really loud point, or destructive interference, if there's no sound there. All right, so armed with this, let's try out an example. So what does a listener hear? Two in-phase loudspeakers, A and B, are separated by 3.2 meters. A listener is stationed at C, which is 2.4 meters in front of speaker B. Both speakers are playing identical 214 hertz tones, and the speed of sound is 343 meters per second. Does the listener hear a loud sound or no sound? Right, so if we want to test this out, right, what we care about is the path length difference for the two speakers. So we care about how far away is speaker A to our listener. call that D sub A. You can use X if you prefer, but I use D just to show that it's a general direction. You could use R if you prefer. So we want that path relative to the path that speaker B takes, right? This is dB. And notice we already know dB. That's that 2.4 meters. So that's really nice that we have that there. What about the distance from speaker A to the listener? Do we know that? Do we have a way that we could calculate it maybe? Notice that we've got a triangle going here. We know the distance between the speakers. We know the distance in front of the speaker to the listener. This is a right triangle. So how can we relate all three sides of the right triangle? That's just going to be our Pythagorean theorem, right? So dA is just going to be the square root of the other two sides. So 3.2 meters squared plus 2.4 meters squared. All right, and that will give us the total distance there. We can then look at the path length difference between dA minus dB, because we know dA is going to be longer than dB. It's a diagonal path. It has to go further. That will give us some number. What we need to figure out then is if that's an integer number of wavelengths or not. So what's the wavelength of this sound? Well, notice they didn't give us the wavelength here. What did they give us for this problem? They mentioned this 214 hertz. What kind of quantity is in units of hertz? That's our frequency, right? So we know the frequency. And what else do we know? We know the speed of sound. So we know V. If we know the frequency and the speed, can we get a wavelength? I think we can, right? Remember that the speed of sound is equal to the frequency times the wavelength. So armed with that, we're now in good shape to actually solve this. So first, here, I'll erase some of this. We need to calculate the path length difference. So that is shown here, where we have dA in the square root here, minus dB. And if you calculate that out, you should get 1.6 meters. For calculating the wavelength, we will divide the speed by the frequency. That will give us lambda. So 343 meters per second divided by 214 comes out to 1.60 meters. Look at this. It's the same number. So the path length difference is exactly the same as one wavelength. So since the path length difference is equal to an integer number of wavelengths, that means that there's constructive interference. That means there is a loud sound. Note, this would have worked even if the path length difference was instead 3.2, right? If it was 3.2 meters, then we would need to divide by the 1.6, and we would get out 2 as an answer. So it would be an exactly integer number of wavelengths. If instead the path length difference was like 0.8, let's get a different color for this. If it was half of 1.6, then if we took that path length difference and divided by the wavelength, our M value would come out to 1/2. And that would give us a sign that this was actually destructive interference. There would be no sound for that. All right, so this introduces the idea of constructive and destructive interference with sound waves. So that is one of the cool effects we'll see with waves, but there's more cool stuff to come because interference, it turns out, can be very interesting.